Hello everyone, welcome to Chem76A. Today we will begin chapter number 11. In this chapter we will learn about ethers, epoxides and sulfides. All these compounds contain a heteroatom bonded to two alkyl chains. In case of ethers and epoxides, the heteroatom is oxygen, and in case of sulfides, the heteroatom is sulfur. So let's begin with ethers. The functional group of an ether is an oxygen atom which is covalently bonded to two carbon atoms which are part of an alkyl chain. The length of these two alkyl chains may or may not be similar. The Lewis structure and bond and stick model of the simplest ether is shown here. In this example, the alkyl chains or alkyl groups are both methyl groups. These kind of ethers are also known as dialkyl ethers because they have two alkyl groups bonded to an oxygen atom. The oxygen atom in the ether functional group is sp3 hybridized, and two of the sp3 hybrid orbitals are used to form covalent bond with a carbon, and the other two sp3 hybrid orbitals of oxygen hold the lone pairs. We know that in sp3 hybridization, the bond angle is 109.5 degrees. In case of dimethyl ether, the bond angle is quite close to the standard value, and actually it is 110.3 degrees. This bond angle may vary if the alkyl groups are bulky. In case we have bulky alkyl groups, the bond angle will be slightly larger than the standard value. As we saw in previous slide, that in dimethyl ether, oxygen atom was bonded to carbon, and this carbon was also sp3 hybridized, and oxygen was also sp3 hybridized. So this was the case in dimethyl ether, as we saw in previous slide. However, in some other ethers, the oxygen can be bonded to an sp3 hybridized carbon also. For example, in case of ethyl vinyl ether. So in this case, oxygen atom of course is still sp3 hybridized, and on the left hand side, the ethyl chain, the carbon is also sp3, but on the right hand side, the vinyl group, so this carbon is sp2 hybridized. So in this case, oxygen atom is bonded to a sp3 hybridized carbon on one side, but on the other side it is bonded to sp2 hybrid carbon. But the hybridization state of oxygen does not change. Oxygen still remains sp3. Let's now learn how to write names of ethers. In many ethers, common names are frequently used. So in order to write the common names, name the groups bonded to the oxygen in alphabetical order followed by the word ether. For example, if I have an ether and on one side I have a methyl group and on the other side I have ethyl group, so I will write these two substituents in alphabetical order. So ethyl comes first, so the name of this ether will be ethyl. then comes the other substituent methyl followed by ether. So the common name of this ether is ethyl methyl ether. Similarly, the common name of this ether is, both the groups are ethyl groups, so the common name is diethyl ether. And in example given here, one side has a methyl group, the other side has a tertiary butyl group, so therefore the common name is tertiary butyl methyl ether. Because of the simplicity of common names, they are frequently used, especially in case of ethers with small alkyl chains such as ethyl, methyl, or tertiary butyl. However, for IUPAC names, we look for the longest chain, or the alkyl chain which is longest will become the parent chain. The rest of the molecule is treated as an substituent. So let me explain with the help of an example. So in this case, we have an ether, and obviously on the left hand side, so this chain is the longest chain, and the right hand side chain is smaller. So in this case, the longer chain, which is highlighted by yellow, is the parent chain, and we can count the numbers of carbon atom. In this case, the number of carbon atoms are 1, 2, 3, and 4. So this carbon chain is butane, and we treat rest of the molecule as a substituent. So how do we name this substituent? Actually, this substituent is OR substituent, and we call this substituent alkoxy. So for example, in this case, we have only one carbon, so therefore the name of this substituent will be methoxy. So hence the name of this particular ether will be methoxy butane. So that's how we write the IUPAC names of ethers. So we look for the longer alkyl chain, that will be the parent chain, and that parent chain is treated as an alkane. And the rest of the molecule, including the oxygen atom, becomes the substituent, and the names of those substituents are figured out with this alkoxy terminology. So if we have only one carbon, then it will be methoxy, two carbon ethoxy, and so on. The nomenclature of cyclic ethers is unique. As you remember, in case of cycloalkanes or cycloalkenes, we just add the prefix cyclo to name any of those cyclic compounds. However, we do not do that in case of cyclic ethers. There are special set of rules to name cyclic ethers. According to IUPAC rules, the presence of oxygen in a cyclic compound such as this one is shown by using the prefix ox, and the size of ring is indicated by different suffixes such as irane, etane, olane, and ane. Irane is used to indicate that the ring size is 3, etane for 4, and olane for 5, and ane for 6 membered ring. So for in our example, in this case, our ring size is 4, and we have an oxygen which is ether. So therefore name or IUPAC name of this substance is ox. Ox indicates that there is oxygen, and then the ring size, which is 4, is etane. So the complete name is oxetane. So similarly, if we have a cyclic ether with 3-membered ring, then the name will be oxyrane. 5-membered cyclic ether name is oxolane, because olane is the suffix for 5-membered ring, and 6-membered ring is oxane. One of the famous cyclic ether is 1,4-dioxane. This is a common solvent which is used in many organic reactions. It's a aprotic solvent. In case we have a substituted cyclic ether, such as this one, when we name these kind of ethers, the numbering always starts from the oxygen. So oxygen will be given number 1, so this will be number 2, 3, 4, and so on. So the name of this compound will be 2-methyl, and then the IUPAC name of the cyclic ether. It's a 5-membered ether, so therefore it is a oxolane. All of these cyclic ethers are known as heterocycles. Hetero means a non-carbon atom, and cycle means it's a cyclic compound. So heterocycles with oxygen and nitrogen are unique molecule, and they are particularly common in organic chemistry because of their importance in pharmaceuticals and other clinically important reactions. Due to high electronegativity of oxygen atom as compared to carbon, there is a permanent dipole in carbon and oxygen bonds, resulting in formation of a partial negative charge on oxygen and partial positive charge on carbon atoms. The existence of these permanent dipoles make ethers polar compounds because these two dipoles are not at exactly 180-degree angle, so therefore these dipoles do not cancel each other out, and hence ethers are polar molecules. Although ethers are polar, but only weak dipole-dipole interactions exist between their molecules. So because of this, low molecular weight ethers are liquid at room temperature, but their boiling points are much lower than alcohols with comparable molecular mass. Remember, in case of alcohols such as methanol, we have hydrogen bonding. So because of hydrogen bonding, the intermolecular forces in alcohols are much more stronger as compared to ethers. Ethers have only dipole-dipole interactions. On the other hand, alcohols have H bonding. So therefore, ethers have low boiling point as compared to alcohols with comparable molecular mass. As discussed earlier, the boiling points of ethers are lower than alcohols of comparable molecular weight, and the strength of dipole-dipole bonds in ethers are not that large. Therefore, the boiling points are closer to those of hydrocarbons of comparable molecular weight. Although ethers cannot form hydrogen bonding between other ether molecules, but they do act as hydrogen bond acceptors. So therefore, they can form hydrogen bonds with protonated solvents such as water. Because of their ability to form hydrogen bonding with water molecules, they are more soluble in water than other hydrocarbons. The most common method to prepare ethers is by Williamson's ether synthesis. This reaction is based on SN2 type of mechanism in which alkoxide ions are used as uh, a nucleophile. The substrate contains a good leaving group, and generally halide, tosylate, or mesylate groups are used as leaving groups. The SN2 attack by alkoxide nucleophile will result in formation of ether, and as I mentioned earlier, this reaction follows SN2 mechanism. While planning this Williamson's ether synthesis reaction, it is important to use a combination of reactants that maximize the nucleophilic substitution and minimize any other competing reactions. For example, if we want to prepare uh, methyl propyl ether, imagine that we would like to prepare this ether. This ether can be synthesized by selecting two different combinations of nucleophile and the substrate. In one combination, we can select methoxy group as a nucleophile. Sodium ion is just a counter ion, and the isopropyl can be our substrate. Isopropyl is a secondary, so it will still give us SN2 type of reaction. So in this case, this reaction may happen and we will end up with our desired ether. The other possibility is, let's call this possibility number 1. The other possibility is that our nucleophile is so in the other possibility we will make the isopropyl alkoxide ion as our nucleophile. So that's possibility number 2. And our substrate is the methyl iodide. In this case again, we will end up with same product. Now, although both of these possibilities will react, but the number 2 possibility is the preferred possibility. The reason is, in number 1, our substrate is secondary. So this is a secondary substrate which will result in a slower reaction. Secondary SN2 is not as preferred as primary. So in the second case, it's primary. So primary is preferred. The other problem is that in number 1 reaction, there is a possibility of elimination reaction because there are two beta positions. So loss of proton from beta position may also result in elimination product. So it is likely that some side reaction will take place in which this elimination product will also form. No such possibility exists in number two reaction because there are no beta carbons, so elimination is not a possible outcome. So therefore, the preferred reaction is the number two reaction. So whenever we plan Williamson ether synthase, we always take the substrate as a primary substrate, and the alkoxide ion can be secondary alkoxide or tertiary or bulky, so that doesn't matter. So in Williamson's ether synthase, the yields are highest with methyl and primary halides, and in case of secondary halides, there will be a competing beta elimination reaction which lowers the yield. And tertiary carbocations or tertiary substrates do not undergo Williamson's ether reaction. In tertiary, only beta elimination reactions happen, so therefore we cannot get the ether. For example, in this case, our substrate is methyl, and methyl is the best substrate we can use, and the alkoxide ion or nucleophile can be a tertiary or it can be a bulky, so that's okay. So this is our nucleophile. So in this case, the yields are best, so highest yield, so best yield possible. But if we try to accomplish the same reaction by flipping the reagent and the nucleophiles, in this case we are using the tertiary reagent and a methyl nucleophile. So this reaction does not produce any ether because elimination is the only possible outcome. So this is not suitable reaction. So therefore, a careful selection of nucleophile and the alkyl halide must be done while planning Williamson's ether synthesis reaction. Ethers can also be synthesized by acid-catalyzed dehydration of alcohols. Diethyl ether and several other commercially available ethers are synthesized on an industrial scale by this reaction. An example of an acid catalyzed dehydration of alcohol reaction is shown here. As we remember that alcohol is a bad leaving group and it is also a bad nucleophile. The presence of acid makes this bad leaving group a better leaving group by converting a hydroxide group to oxonium ion, which leaves as a water molecule. We will learn about the mechanism of this reaction in next slide. Let's try to understand the mechanism of acid catalyzed dehydration of alcohols. This dehydration reaction is an intermolecular reaction in which a primary alcohol such as ethanol will react with another alcohol molecule and the product will be an ether and water. We may consider this reaction as if the OH from one alcohol is combining with hydrogen of the other alcohol, and this H and OH results in formation of water, and then rest of the molecule combine with each other to form ether. This is not the mechanism, this is just how the reaction looks like. So let's take a look at what steps are involved in this reaction mechanism. As we already know that hydroxyl group is a bad leaving group, and addition of a proton to hydroxyl group results in formation of oxonium ion, which changes the hydroxyl group from bad to a good leaving group. So therefore this reaction is carried out in presence of an acid. The most common acid which is used in this case is sulfuric acid, and the reaction is carried out at elevated temperatures such as 140 degrees Celsius in this case. So the step one of this reaction mechanism is addition of a proton to one of the alcohol molecule. And this proton transfer step is a fast and reversible step, and it will result in formation of an oxonium ion. Plus the conjugate base of the acid. In second step, another alcohol molecule attack the alcohol with oxonium ion, which was generated in step number 1. Remember, this oxonium ion is a good leaving group, so therefore this attack by weak nucleophile can also produce this reaction product. Normally in SN2, weak nucleophiles are not preferred, but because oxonium ion is such a good leaving group, therefore even a weak nucleophile such as alcohol can result in this product. And this is SN2 mechanism step, and it will result in formation of a precursor to an ether. So this is not an ether yet. It's a precursor to our final product. In the final step, a proton transferred from the newly formed oxonium ion, shown here, results in formation of ether, and this step also creates a hydronium ion, which is the acid part. Remember, this reaction was catalyzed by acid, and at the end the acid molecule is generated back. Hence the acid in this reaction is a true catalyst. As we know, true catalysts are those substances which themselves do not participate, but they only facilitate the reaction. The yields of ether synthesis from acid catalyzed dehydration of alcohols are highest for symmetrical ethers, such as diethyl ether, shown here. For asymmetrical synthesis, such as methyl ether, or methyl ethyl ether, so these kind of ether synthesis yields are low. because two different product formations are possible. And this reaction works the best only for primary alcohols. For secondary, the yields are low. The reason is the competing elimination reactions, which were discussed in the previous case also. And tertiary alcohols do not work in this reaction. Another method to synthesize ethers is by acid-catalyzed addition of alcohols to alkenes. The usefulness of this method of ether synthesis is limited to the interaction of alkenes that form stable carbocation, and by using methanol or a primary alcohol that is not prone to undergo acid-catalyzed dehydration. So because of these limitations, this method of ether synthesis is not very suitable. An example of this reaction is the commercial synthesis of tertiary butyl methyl ether. So tertiary butyl methyl ether is an ether in which one alkyl chain is a methyl group, and on the other side of oxygen we have a tertiary butyl group. So this ether is known as tertiary butyl methyl ether. By the way, tertiary butyl methyl ether is its common name, and its IUPAC name is 2-methoxy 2-methyl propane. And this ether can be synthesized by addition of methanol to 2-methyl 1-propene. As we know, in addition reaction, the pi bond cleaves and the bond between the heteroatom and hydrogen cleaves, and hydrogen goes to the carbon atom with more carbons, and then the other part of addendum goes to the adjacent carbon atom, and it will result in formation of this ether. Can change the colors. The tertiary butyl methyl ether is abbreviated as MTBE, where M stands for methyl, T is tertiary, B is butyl, and E is ether. You probably already know that all gasoline sold in our country contains 10 to 15% alcohol in gasoline. The reason why alcohol is added is to promote the oxygen content of gasoline, which ensures the complete combustion of gasoline and hence cleaner emissions. At one point, MTBE was used as the additive to gasoline, A blend of 15% MTBE was actually better than alcohol. So it would ensure that gasoline completely combusts, and it was doing its job really well. Now, the problem with MTBE is that it is much more soluble in water, and because in gas stations the gasoline is stored underground, and many times from those leaky underground tanks, MTBE would leak and it would go and mix with underground water supply. So MTBE was found in many lakes, many other local water district water supplies, and the amount of MTBE in those lakes or in water supplying containers was found to be much higher than the safe limit for taste as well as health. So that's why MTBE is no longer used as an additive to gasoline. Acid catalyzed addition of an alcohol to an alkene follows E2 mechanism. As this reaction is catalyzed by an acid, so therefore alcohol hydroxyl group will grab a proton from acid, which would convert the hydroxyl group to oxonium ion. This oxonium ion will transfer its proton to the alkene, which will result in formation of a carbocation. Remember, only those alkenes work which result in a tertiary carbocation formation. This is a slow step and it's a rate determining step, and it will result in formation of a tertiary carbocation. Plus the alcohol. In the next step, another alcohol molecule acts as a nucleophile and it attacks the tertiary carbocation. And this attack results in formation of a new oxonium ion. In the final step, a proton is transferred from the newly formed oxonium ion to solvent, which is methanol in our case, and it will result in formation of an ether. So this was the oxonium ion which was formed in previous step. A solvent molecule, in our case solvent is methanol, will accept a proton and it will result in formation of tertiary butyl methyl ether. So this is MTBE plus a protonated methanol molecule. Now that we have learned the methods to synthesize ethers, let's talk about reactions of ethers. Just like alkanes, ethers are also resistant to chemical reactions. They do not react with common oxidizing agents such as potassium dichromate, chromic acid, or potassium permanganate. They are also stable towards strong bases. And except for tertiary alkyl ethers, they are not affected by most other weak acids at moderate temperatures. Because of their good solubilizing properties and general inertness towards chemical reactions, ethers are excellent solvents to carry out many organic reactions. One of the very few reactions shown by ethers is cleavage reactions. Ethers are cleaved by halogen acids to an alcohol and haloalkane. So this reaction is opposite of the synthesis of ethers by SN2 reactions. In this cleavage reaction, the bond between oxygen and one of the alkyl chain will break, and the bond between hydrogen and halogen will break. The halogen will create a covalent bond with the alkyl group, and hydrogen will bind with the oxygen to create alcohol, and the other product will be alkyl halide. This cleavage reaction requires both strong acid and a good nucleophile. So therefore, a concentrated aqueous hydroiodic acid or concentrated hydrobromic acid are perfect acids which can be used in this cleavage reaction. Cleavage by concentrated HCl is less effective because chloride is a weaker nucleophile in water than iodide or bromide. The values or the numbers shown in parentheses are the percentage yield values, and as you can see, the maximum yield is obtained when we use the most concentrated acid, which is HI. The percentage yield in case of HCl is the lowest. Let's take a look at specific example of this cleavage reaction of ethers. For example, if we react a dipropyl ether with concentrated acid such as HBr, we know that it will result in formation of an alcohol, which is propanol in this case, and it will also result in formation of a alkyl halide, which is bromopropane. If we use excess hydrobromic acid, or if we use 2 moles of hydrobromic acid, then the alcohol which is formed in the first step will further react with the hydrobromic acid, and it will result in another molecule of bromopropane. Plus water. So therefore we can say that if we have only 1 mole of acid and 1 mole of ether, then the product will be an alcohol and an alkyl halide. But if we use 2 moles of acid or excess of acid, then the product will be 2 moles of alkyl halide and water. The mechanism of acid catalyzed cleavage of dialkyl ethers depends on the nature of the carbons bonded to oxygen. If both the carbons bonded to oxygen atoms are primary, for example, in this case, the carbon atoms highlighted in yellow are primary, then the mechanism will follow SN2 reaction in which the halide ion will act as a nucleophile. Otherwise, the cleavage will follow SN1 reaction. So in this case of diethyl ether, because these carbons are primary, so therefore cleavage by HBr will follow SN2 type of reaction. And if we use excess of HBr or 2 moles of HBr, then the resulting product will be a bromoalkane and water. So let's take a look at this mechanism. So as we learn that this mechanism is going to follow SN2, but because the alkoxy group is not a good leaving group, so therefore the first step involves the transfer of proton, which will convert the ether oxygen to an oxonium ion. So the first step involves the transfer of proton. This step is a fast and reversible step, and it is not the rate determining step. In the second step, halide ion will act as a nucleophile, and it will attack the oxonium ion which was generated in previous step, and this nucleophilic attack will result in formation of an alkyl halide and an alcohol molecule. Because this reaction is SN2, so this is a backside attack. So bromide or the nucleophile will attack from the back and leaving group, which is the entire alcohol molecule. So this entire molecule is the leaving group, and this reaction will result in formation of an alkyl halide and an alcohol. So if another mole of HBr is present, then the alcohol, which is generated in step number 2, will react again, and it will form another haloalkane by another SN2 reaction. Tertiary allylic and benzylic ethers are particularly sensitive to cleavage by halogen acids, and these kind of reactions often occur under quite mild conditions. For example, tertiary butyl ethers are cleaved by aqueous HCl at room temperature. Remember, HCl is not a good reagent for primary alkyl ethers, but in this case, HCl is enough, or HCl is a good reagent to perform this cleavage reaction. So these kind of cleavage reactions involving tertiary allylic or benzylic ethers undergo reactions by SN1 mechanism. Let's take a look at one of the example. In this case, one of the alkyl chain is a tertiary butyl group, and if we react this ether with HCl, the first step will be a proton transfer step, which will result in a protonated ether. The formation of protonated ether will be followed by a slow leaving loss of leaving group step, and in this step the alcohol molecule will leave, and it will result in formation of a carbocation and an alcohol. The resulting carbocation is a tertiary carbocation, and we know that tertiary carbocation is a stable or more stable carbocation. And because this reaction is a SN1 kind of reaction, so even a weaker nucleophile such as chloride ion is enough to give us a product. Extreme care must be taken while working with ethers in any lab. There are two kinds of hazards which are primarily associated with the use of ethers. First is that they have low boiling points, especially the low molecular weight ethers. Their boiling point is very low and they are highly flammable. So combination of low boiling point and high flammability is a dangerous combination. So consequently, open flames and other electrical appliances with sparking must be avoided when ethers are being used. The other hazard while working with ethers is that they react with oxygen to form hydroperoxides. Hydroperoxides are formed when ethers react with atmospheric oxygen at a carbon hydrogen bond adjacent to either ether oxygen to give hydroperoxides. For example, in this molecule we have two carbon and hydrogen bonds which are right next to oxygen. So in either of these two bonds, the atmospheric oxygen will react and this oxygen will get incorporated in this bond, resulting in formation of hydroperoxides. These hydroperoxide formation reaction follows a radical chain mechanism, and these kind of compounds are highly explosive. So therefore, when ethers are stored, they are stored in a bottle which is completely full, so that no atmospheric oxygen is present within the same bottle. we avoid storing ether in a half full bottle, because half full bottle means the remaining half has oxygen, which may result in formation of hydroperoxide. Also, ethers are stored at low temperature, which um, also prevents the formation of hydroperoxides. In this section, we will discuss about one of the most important concepts which is used when we plan any organic chemistry synthesis reaction. When dealing with compounds containing two or more functional groups, it is necessary to protect one of them to prevent its reaction while reacting at the other functional group. Let me give you one example. Suppose we want to carry out this reaction. Now, this reaction is similar to the reaction which we studied in the chapter of alkynes. In chapter 7, we learned that terminal alkynes are uh, acidic, and the proton from this terminal alkyne can be easily removed by a strong base such as amide. So if we use sodium amide, it will result in formation of this carboanion, and this ion is a strong nucleophile, and if we add alkyl halide to it, and then this will result in formation of a longer alkyne. So terminal alkynes are acidic. In this case, it's acting as an acid and it's a base. So a proton is transferred to the base. So now we can propose a similar reaction in which we may propose that, okay, let's use sodium amide first, and this sodium amide will remove the proton, so this proton will go away, and then we will add, after the proton is removed, and then in the second step we will add ethyl iodide, and we should get this product. But there's a problem, and I'll explain the problem in next slide. The problem is the pKa value. For the proton connected to the carbon-carbon triple bond, the pKa value is 25, and the hydrogen atom connected to the alcohol, the pKa value is 16 to 18. So therefore, the base remains the same, but the acid, there are two acidic protons. So both of this is also acid and this one is also acid. But the problem is, because hydroxyl ion has low pKa value, this acid is strong. So even though we would like our base to react here, but this reaction is not possible because base will react with the strongest acid available. So therefore, instead of reacting with the proton at alkyne to give us alkylide ion, which will continue to give us our desired product, we will end up with this reaction. And this product will not give us the desired reaction in which we can get. So this reaction now is not possible. So presence of this alcohol is interfering with our reaction scheme. So in order to perform the reaction which was proposed in previous slide, we need to take care of this alcohol, or we need to protect this alcohol group so that this alcohol group no longer is available to the reaction. And once we protect this alcohol group, then the rest of the reaction will proceed as we planned in previous slide. So this is the concept of protecting the functional groups. Silyl ethers are excellent protecting agents for alcohol functional groups. And in next slide, we will learn about what are silyl ethers and how do they protect the alcohol functional groups. A good protecting group must be able to add easily to the sensitive group, and it must be resistant to reagents used to transform the unprotected functional group, and the good protecting group must be removed easily to regenerate the original functional group. There are many different protecting groups available, but in this chapter we are only going to discuss trimethylsilyl and other trialkyl silyl ethers as protecting groups for hydroxyl functional group. So all of these protecting groups only protect hydroxyl functional group. There are many other protecting groups available which will protect different functional groups such as aldehyde, ketones, but we are not going to discuss those for now. Silicon is present in group 4A just below carbon in the periodic table. Just like carbon, it also forms tetravalent compounds as shown here. For example, carbon forms carbon dioxide and silicon forms silicon dioxide. A compound similar to methane is silane. In methane, carbon is bonded to 4 hydrogens, and in silane, silicon is bonded to 4 hydrogens, just like methane. Because of these similarities in many other properties, silicon is also able to form covalent bonds with carbon atoms. For example, in this molecule, silicon is bonded to 4 other methyl group, and the name of this compound is tetramethylsilane. The compound which is used to protect the hydroxyl group by converting the hydroxyl group into silyl ether is this one, chlorotrimethylsilane. Chlorotrimethylsilane reacts with alcohol group and convert alcohol function group into silyl ethers. And these silyl ethers are inert towards most of the reagents, and hence the reaction may continue to occur at other part of the molecule and the silyl ether part remains unaffected. So using this chlorotrimethylsilane, the alcohol functional group is converted into trimethyl silyl ether. So in this reaction, what happens is the proton from the alcohol and the chloro from chlorotrimethyl are eliminated, and it results in formation of a trimethyl ether. So it's called ether because it has a oxygen, and silyl means it is oxygen is bonded to silicon. So trimethyl ether. This reaction is carried out in presence of tertiary amine. The function of this tertiary amine is to neutralize the acid which is formed during this reaction. Trimethyl chloride is abbreviated as TMSCl. And TMSCl is one of the most commonly used protecting group for alcohols. In TMSCl, silicon is bonded or connected to methyl groups or 3-methyl group. Other common silyl protecting groups include TES and TIPS groups. So in TES, we have triethyl. So ES means triethyl silyl chloride, And in TIPS, we have triisopropyl silyl chloride or TIPS chloride, or TES or test chloride. All of these behave similarly. So they react with alcohol and they remove proton from alcohol and chloro from these protecting group. As a result, they form a silyl ether. If we remove one of the methyl group and add a tertiary butyl group, uh, and keep the other two methyl group the same, this results in formation of another protecting group, which is known as tertiary butyl dimethyl silyl chloride. And this uh, protecting group is much more stable than the trimethyl silyl uh, chloride, and this one is frequently used in organic synthesis reactions in which we have to protect hydroxyl functional group. As we learned earlier, a good protecting group must add easily to the functional group, and silyl chlorides uh, can add to hydroxyl functional groups at room temperature by just simply shaking the silyl chlorides with the alcohols. The second property of a good protecting group is that it should remain unreactive in most reaction conditions. So silyl ethers are unaffected by most oxidizing and reducing agents, and they are stable to most known aqueous acids and bases. And tertiary butyl dimethyl uh, silyl ether group is stable in aqueous solution within the pH range of 2 to 12, which makes it one of the most widely used alcohol protecting group. So because of these properties, uh, we can say that silyl uh, chlorides or trialkyl silyl chlorides are extremely good protecting group. Now the final property is that these protecting groups should uh, come off easily from the alcohol, and they should regenerate the alcohol functional group back. So now removal of silyl protecting group can be carried out by treatment with fluoride ion. So fluoride ion is generally supplied in form of a tetrabutyl ammonium fluoride in THF. So once the silyl ether is formed, so remember that this part was alcohol, but now this alcohol part is protected by this silyl protecting group. So this entire green thing is the protecting group, which is protecting the alcohol functional group. And now we want to generate the alcohol back. All we need to do is supply a fluoride ion, and fluoride ion is supplied in form of this compound. It is tetrabutyl ammonium fluoride in presence of THF. THF is just a solvent, and the silyl protecting group comes off easily, and it gives our alcohol back. Now, why this reaction is so easy and fast? The answer is the bond dissociation energy. The energy required to break the silicon and oxygen bond is only 368 kilojoules per mole, but the energy released when silicon and fluoride bond is formed is 582. So therefore, going from uh, this to this, it's large exothermic. So because of this large amount of net negative energy released, the reaction is favorable towards the product. So hence the silyl protecting group can easily be removed. So now let's see how we can accomplish the same reaction using the silyl ethers as protecting group. Remember, we learned previously that if we do not use any protecting group, the reaction occurs at OH group instead of this hydrogen. So in this case, we will again start with the same alkane, and first we need to protect the hydroxyl group. So we will react the hydroxyl group with trimethyl or any of the other one. We can use triethyl also, TIPS also, but let's stick with trimethyl silyl chloride, and in presence of triethylamine, and this will result in formation of a silyl ether. So let me use different colors so that you can see where the molecule or where the different units are coming from. So now our alcohol functional group is protected and it no longer has any proton. So no proton exists on this side. So therefore, when we add a strong base to it now, which was sodium amide, so the amide is the base part of it. It cannot react with the alcohol functional group because there is no proton available. So in this case, it will remove the proton from the alkyne part, resulting in formation of a carbanion, which is a strong nucleophile. And the reaction of this strong nucleophile to an alkyl halide will result in formation of the final precursor to the final desired product. The silyl ether is still there, so the final step is removal of the protecting group or the silyl ether part, and this can be easily removed by reacting with the fluoride source. In this case, it's the tetrabutyl ammonium fluoride. And that's how we can complete our synthesis reaction without any interference from the alcohol functional group.